let's just go through another test paper for THERMO KK for session 2021 semester 2. So let's just go through the first question and see if there's anything different from the last one that we discussed. Here the first question says calculate the molar volume of phenol vapor at 763.15 K and 70 bars using the ideal gas equation, then the RK, and then generalized compressibility factor correlation. Okay, so as we all know, the ideal gas equation is of course PV equals ZRT, but we are assuming Z equals to 1, hence PV equals to RT. I think I've already covered why Z equals to 1, because we are assuming that the intermolecular forces between the molecules are negligible, hence Z equals to 1. And also the Redlich-Kwong equation, I believe I've also gone through that. Let's just find. Yep, it's this one, or there's another one, I think. Alright, never mind, let's just go through my working later. So of course there will be the parameters that you guys have to pay attention to. I think you guys can just bookmark the pages on your textbook and then look at the parameters assignment for the EOS for Redlich-Kwong. And then the generalized compressibility factor correlation. I believe this is quite new to you guys because I've never discussed this on the previous paper. This is actually the Z equals to Z0 plus Z1, I believe. Yep. So the W here, it is actually the eccentric factor. Yeah, the eccentric factor. This one you guys can find on this table. Let me see. I think it's in table B. Yeah, in the table B1, the properties of pure species. So for phenol vapor, you guys can find the eccentric factor here. Yeah, the phenol is 0.444, and then the Z0 and Z1 you guys can find on table D, I believe. Let me see. Yep, on table D. But you guys have to pay attention when using the table D, because table D1 up to table D3, they include, table D1 to D4, it includes substances in both liquid and vapor states. If you notice here, they said the numbers printed in italic are liquid phase properties. So from here up until, yeah, I think it's this one. Yeah, basically whatever, until basically all the numbers printed in italics are for liquid phase. So just pay attention to that, because our substance of phenol is in vapor state. So just pay attention to that, so you guys don't use the italic numbers. It's just like a double check to whether you guys are using the correct numbers or not. So yeah, this is where you get the values for Z0 and Z1. You guys need to use interpolation to get the values, the exact values for this. Next, this is just mostly theory. I'll go through that later because it's quite long. So yeah, let's just do first question. Let me go back to table B. Okay, so I think I don't really have to go through really deeply for ideal gas equation, since it's pretty straightforward. You just have to substitute the values given from the question. Yeah, and then you'll get 906.4. For this question, one trick I learned to check whether you are in the correct direction after you finish doing all these three equations, your value of Z, this one and this one should not really be the same value, but they should be almost the same. Like their values shouldn't differ that much. Like here is 0.6588 and here is 0.6321. So their values are not the same, but they don't differ that much. And also for volume as well. Here is 597.14 and here is 571.03. So that's just one trick I learned, that whether you guys are in the correct direction when applying the equations, is that your values of Z and V shouldn't differ that much. So if one of your values from your equation differ really big, that means you must be doing something wrong, or you guys might substitute a different value, I suppose. So anyway, for question B, the Rayleigh-Kwong equation, yeah, the equation should be this: Z plus 1 beta minus Q beta times Z minus beta over Z plus Q beta times Z plus sigma beta. So the parameters are here. So for beta, it's just omega times PR over TR. As usual, your value of PR, to get PR is just P over PC, and TR is T over TC. TC you guys can find from the appendix B from here. For phenol, the PC is 61.3 and TC is 694.3. And then just finding your PR and TR, as well as your ATR from the parameters. Let me see where the parameters. Yep. So for your ATR, it's just temperature reduced power of -1/2, and then your sigma is 1, epsilon 0, omega is 0.08664, and your phi is 0.42748. Yeah, just by listing up all the parameters given in this table, you guys can just substitute the value. Of course, for Rayleigh-Kwong, actually for any cubic equations of state, and also for all equations of state, cubic equations of state specifically, you guys have to do iteration for both Z, either Z or V. So if you want to find V first, then you have to do iteration to get the value for volume. And if you guys want to start with Z, then you guys have to do iteration for Z until you get a constant value. So yeah, I think I've sent this PDF before, but there's a minor correction, because if you see here, before this it was just Z minus 0.09 over Z plus 0.09. So there's a little mistake there. It actually should be another Z here, because if I put epsilon as 0, Z will still be there. So I didn't put another Z here, so my calculations were a bit off, and I get a very huge value for volume. So that's just one indication that you are in the wrong direction. So yeah, you guys have to pay attention to this. I corrected it, so you just want to tally with the PDF I've given before. Yeah, moving on. As usual, we are starting with Z equals to 1, since we are assuming that the first iteration starts off with ideal gas state. So Z equals to 1, and then we'll get the initial value for our first iteration, which is 0.7674, and then by subbing in back into the Z, and then by pressing answer multiple times, you'll get a constant value. Actually, the iteration should go more than 5, I think up to 10, but I was just too lazy to write down every values. But during exam, I feel like you might want to write down fully up to 4 decimal places, just to make sure you guys get the most accurate value as possible. But I just shorten it to just 2 decimal places, because well, I'm too lazy to write down every single values. So I assume it's 0.63, and then by plugging back into PV equals ZRT, you get about 571.03. So now let's move on to generalized compressibility factor correlation. Yeah, the general formula should be this. Again, Z0 you guys can find from table D. Let me just go back to table D. Yeah, and Z0 from here as well. Your eccentric factor is from your pure properties table. You get 0.444 for your eccentric factor for phenol, and Z1 is also, you guys can obtain from table D. T3, I believe. Yeah. So, okay. So you guys have to find your PR and TR first. I already found in when I was doing the relish Kwong, so I just used back again. Okay, so let's just, the one method of reading this table is we have to look at both headers here. So first we look at PR. PR lies between 1 and 2, and TR lies between 1.1 and 1.05. But here's the thing, you can't really pick a value here. You guys can't pick, like, I don't know how to interpolate. I feel like if I choose two numbers here and also two regions here, I can't really interpolate. Can I don't think so. So I just round off either one. I believe the closest I can round off is, of course, your TR is 1.0992. I feel I can round it off to 1.1 because yeah, I feel like that's the closest value to 1.1. If I can't really round off 1.14 to 1 because the values are a bit too accurate for me to really round it off to 1. So the closest is just I can round off to TR for 1.0992 to 1.1. Yeah. So just basically just your normal interpolation to get the value for Z0 and also for Z1. I believe you guys know how to interpolate, so I don't really have to go through again. Then once I get your value of Z0 and Z1 and also your eccentric factor, this W phenol here, then I'll just plug it back into the general equation to get 0.6588. And then, well, once I found the value of Z, I'll get the value for volume. So the next question is, they said, if the actual experimental value of volume is not given, predict which of the above equation is the most accurate. So let's just see here. For Lee Kessler, yeah, okay. Yeah, okay. So to know which one is the most accurate from the actual experimental value from either these three, so let's look at the ideal gas. Since ideal gas equation, we are assuming that the intermolecular forces are negligible, so Z equals to 1, right, in ideal gas equation. So but in real gas state, in actual experimental value, we are taking Z into account. We are actually taking intermolecular forces into account. So obviously we know that ideal gas equation is wrong, or it's not technically wrong, it's just that it's not as accurate because we are treating intermolecular forces as something that is negligible, so it's not actually as accurate as you can get. So obviously it's not ideal gas equation, so we are left with either Bradley-Kwong or generalized compressibility factor correlation. So yeah, so one thing that the Redlich-Kwong equation or the cubic equations of state does the same thing as generalized compressibility factor correlation, is that they are both accurate in terms of they are actually taking intermolecular forces into account. They don't neglect it, so they are both accurate, but then it comes to the state of pressures. So the generic cubic equations of state, they are accurate up to a certain point of pressure. Once it exceeds a certain amount of pressure, your value of Z is not really that reliable. I think it's up to a certain value, but it is only applicable for low pressure conditions, except for generalized compressibility, my bad. So yeah, now we look at the system. It says it is up to 70 bars. 70 bars is pretty high pressure system. So when you are using Redlich-Kwong equation, it is not as reliable anymore, since the situation is in high pressure. So yeah, So now we can deduce that generalized compressibility factor correlation is more accurate since the pressure is high, and also the PR value is also within the range of lesser than 3.0 in the graph of Z0 against PR. So let's just look at the graph Z0 against PR. Yeah, so as PR reaches the value of more than 3, it starts to not be reliable anymore for gases, especially if you look at the graph. It starts to go way above the region, so it is not as reliable. There's also limitations to generalized compressibility graph. Once it exceeds PR of above 3, then it starts to get a little weird and unreliable. But since our reduced pressure is within the range, which is 1.1419, which is lesser than 3, the results are still reliable enough to use that equation. Again, just to repeat, ideal gas equation is not as accurate because we are neglecting intermolecular forces, and also Rayleigh-Kwong, it is reliable, it is accurate, but since the system is in high pressure, the results can be a little unreliable. But for generalized compressibility, it is reliable up to a reduced pressure of 3. But since our system has reduced pressure of 1.1419, it is still within the range, so it produces a reliable result. So our most accurate should be generalized compressibility factor correlation. Hi, welcome back. Let's just go through question 2. This is heat of reaction question. So as usual, let's just go through the question fully in detail so that we don't miss out anything. So let's just look at the statement. In industrial conditions, ammonia oxidization produces nitrogen oxide by the reaction. 4NH3 gas plus 5O2 gas produces 4NO gas plus 6H2O gas. Okay, so we know that both products and reactants are in gaseous state, so there is no change of state. Next, the feed stream enters the reactor with 10% excess dry air at 25 degrees Celsius. So we know that T inlet is 25 degrees Celsius, and there's also 10% excess dry air. Dry air meaning there's only O2, N2, there is no H2O. So I'm just glad that it happened. There's 79% N2 and 21% O2. And the reactor operates adiabatically with no side reactions. Okay. So for the purpose of calculation, sketch the hypothetical process path and state assumptions. Okay, let's just go through the assumptions first. So just like energy balance you guys learned from previous semester, we know that for open system it's Q minus WS equals to delta H plus delta PE plus delta KE. WS meaning work shaft, Q is the heat, and H is enthalpy, PE potential, KE kinetic. So we know that there is no work done to the system, so yeah, no work done to the system, and there is no change in elevation, there is no change in velocity. So that is our assumptions. So if we assume that there is no work done to the system, WS can be 0. If there is no change in elevation, PE can be 0. If there is no change in velocity, KE equals to 0. So what is left is Q equals to delta H. One more thing is that all constituents are ideal gases. Since we are using table C1 to calculate the change in temperature, the heat capacity of gases in ideal gas state, we need, in order for us to use this table, our constituents, our components, our chemical species should be in ideal gas state. So that should be one more of our assumption. All constituents are ideal gases in order for us to use table C1. So yeah, just remember these 4, everything should be okay. Next is the hypothetical process path. So as usual, we are starting with our products, which is 4NH3 plus 5O2, just ammonia and oxygen gases, and our starting temperature, they say, is at 25 degrees Celsius, so just convert it to Kelvin. and you'll get 298K. And then there is no change in temperature. They didn't say any final temperature, so we can assume that there is no decrease or increase in temperature. So our next path should just be to produce our product, which is nitrogen oxide plus water at the same temperature of 298K. And then for the final path is, of course, when we are producing ammonia, we don't know whether it's a exothermic or endothermic reaction, but there should be a change in temperature, which is the final temperature, but we don't know. So we can just label it as TF unknown, but there should be enthalpy for the product. So there should be another path, and then yeah, there should be just only two paths. And then here should be your delta H. Yeah, that should cover the whole process path. So next, what is the final temperature if 100% conversion can be achieved? 18 marks. Please do it properly, because 18 marks is quite huge for just one single question. So just don't leave it empty. Try to at least goreng something, so you guys can at least get some marks. Just the table alone is enough to get some marks out of 18 marks. So as usual, we are setting our basis as 4 moles of ammonia at feed. Just like previous video, I use assumption of 4 moles because I use a stoichiometric coefficient for the sake of simplicity. But if you guys want to use 1 mole, it's up to you guys, but I wouldn't recommend it, because then your stoichiometric ratio would be a little harder. Not really harder, but yeah, if you guys are smart enough to do it, then sure. But just for the sake of safety, just use the stoichiometric coefficient that they give. And also, what else? The 10% excess dry air, and also 100% fractional conversion. Oh yeah, one more thing that you guys have to pay attention to is 100% conversion. In previous video, we did 85% conversion. So which means 85% conversion means that only 85% of the product, only 85% of the reactants are converted into products. But here, it is very simple, because they said 100% conversion, which means that 100% of our reactants are converted into products. So there should be no reactants in the output stream. So that should be simple. But that's not it. There should be excess O2 at the output, because dry air is in excess. So there is excess of oxygen. So yeah, first thing first, you guys have to construct a table, which is the substances involved in this reaction, and the number of moles at feed, number of moles of that is reacted in this equation, in this reaction, and then number of moles at output. So first substance is, of course, ammonia gases. Since we assume 4 moles of NH3 is at feed, then we put 4 moles here. And then for O2, there is 5 moles if we use stoichiometric coefficient. So 4 moles of NH3 reacts with 5 moles of O2. So there is 5 moles. But one thing that you guys have to pay attention to is the 10% excess dry air. So actually, if you are very curious about why I do 1.1 times 5, is because actually it's to get O2 excess. The calculation for 10% excess dry air is actually just hold on, it's just 5 plus 0.1 times 5, which you'll get, because it's in excess, right? So you have to add up the percentage to the initial value given. So 5 plus 0.1 times 5, you get 5.5, which is essentially same as 1.1 times 5. It's the same thing. Instead of doing like a whole lengthy calculation, you can just do 1.1 times 5. So yeah, you get 5.5. And for N2, we are using ratio. We are not using any complicated calculations, which is just 79 over 21 to get 20.69 moles. And we know that there is no accumulation, so there's no nitrogen oxide and there's no H2O at the feed stream. So N reacted, number of moles reacted, we have no NO and H2O reacting, they are just products. So we can just put this as 0, and then they said 100% fractional conversion, right? So 100% of number of moles of NH3 is completely reacted. So number of moles reacted is 4, but the number of moles reacted, we have to do stoichiometric calculation. So if 4 moles of NH3 is reacted, then 5 moles of oxygen is reacted. So which leaves us as 0.5 moles of oxygen at the output, which is just 5.5 minus 5. And M2 is not involved in reaction because it is an inert gas, so just 20.69, the same number of output is the same number of at feed. And by stoichiometric coefficient again, which is 4 and 6 for NO and H2O. So pretty simple. For HF, you guys have to look at the heat of formation. Yeah. Hold on. Yeah, for heat of formation, let's just find it again. Yeah, okay. So just like previous paper, for heat of formation, you guys have to times with the stoichiometric coefficient, but for CPDT, for the value of A, B, D, you guys have to times with the number of moles for that substances. So heat of formation using the stoichiometric coefficient, my bad, I was looking at the different stuff, different table. So yeah, NO gas is 9250, for water, for gas is negative 241,818, and then minus 4 times the product, which is NH3, minus the reactant, sorry. Yep. And also for oxygen, it is an inert gas. I mean, it is what do you call that? Inert gas? No, I forgot the term, but if it's 0, so you guys said you don't have to find it in this table because it's not there. And by simple maths, just minus, and you get this. So, and next is we have to find the change in temperature, the enthalpy produced when there is the change in temperature from 298 K to an unknown temperature. But the question says what is the final temperature. So we are assuming that the temperature that this system reaches is at max. So one condition when our system reaches max temperature is this one. At T max, our H is equals to 0, our enthalpy is equals to 0. This is what I mean, equals to 0 for T max. So by simple algebra, which is delta H, we know delta H is HF298 plus HP meaning the CPDT, the change in temperature from 298 to T max. Since we don't know HP, we can just put it as HP, and we know that delta H is equals to 0, so delta HP is equals to 905,468 joules. So but it doesn't stop there, because HF for HP, it is, we need to find the final temperature, right? So we can't just leave it like this, because this is the value for the enthalpy, it's not value for temperature. So first we have to find the summation for A and B and D for ideal gas state, to calculate the change in temperature. So again, this is just a method of finding the values in table. I'll get the summation, and then let's just plug in. Okay, so this is where it gets a little bit tricky, and we know that HP, actually to derive this, is pretty simple. HP is integration of CP over R, I think. No, it's actually R over CP. R integrate CP dt. Yeah, so you get HP equals to R CP T final minus T initial. So by rearranging the equation, you'll get T max, T final, which is T max, equals to delta HP over R and CPH plus T0. That's it. So this is how I get this one. So if the equation is in the textbook, so you don't have to waste your time deriving it. But if you are in a hurry and you are and don't want to waste time looking through the textbook, you guys can derive it by yourself. So yeah, and then I'll get this whole thing. Yeah, and then you get this complicated equation. I recommend you guys to just bookmark this in your textbook. Yeah, I really recommend you guys to just bookmark in your textbook so you don't waste time finding it, because deriving it to this up to this point, it's not tricky, but it's going to consume a lot of time if you guys are not really expert in deriving equations. So yeah, as usual, if we have value of A, which is this one, 104.0507, and we have value for B, which is 0.0237, and we have value for D, which is 149610. So it's just a matter of plugging in values. Except we also have value of T0, T naught, but we don't have value for T. T is what we are iterating. Okay, so we have to start our iteration with the initial temperature of 298.15 K, and then yeah, and then you'll get this. Your first iteration is 1263.65. So what we're going to do is we're going to sub in back we're going to sub in back this 1263.65 to this one, and also to this one. Yeah, and then just by I think I've shown you how I press my calculator. So just keep pressing your answer till you get a constant value of 1190.06 K. So this is where I stop my iteration, and then yeah, this is your T final actually, and then you just convert back to Celsius and you get 896.91 degrees Celsius. Yeah, it's pretty much just that. If you guys have any doubts or questions, if I'm going too fast, just tell me if you need more further explanation, but I feel like that's it. There's nothing else important.